so much. So thank you. My name is Nouamane Tazi. I'm a machine learning engineer at Hugging Face. I work at the distributed training team, currently leading the Nanotron library, the library that we use for training like StarCoder, SmallNM, etc. And today I'm going to be presenting to you or demystifying the 5D parallelism. So today we're going to try to see data, tensor, context, pipeline, and expert parallelism in 20 minutes. So good luck. Yeah, so some small introduction. People are training large models. They train them for longer on more data. And they have longer and longer contexts. What's our toolkit? So in our clusters, in our clusters, we're going to work with GPUs or actually any kind of hardware, but they mostly come in like racks or in nodes. And the node contains typically 4 to 8 GPUs with a very good intraconnect and a cluster combining a lot of these nodes with a lower interconnect. And this is important, like you can notice how the interconnect is almost 20 times faster. So we need to use the NVLink or the intraconnect efficiently when we're going to do the communications on the... Are we doing something?
Like again.
Test. Okay, so...
Everybody's celebrating against your face.
And to see that, so we have, as we said, nodes of 8 GPUs, and everything is interconnected. And the high intraconnect is within one node. And then once you go past that node, then you're going to go through the slow Ethernet. So we need to take that into account when we're going to do a bunch of trainings on a lot of GPUs. So let's start with one GPU. So training on one GPU is pretty simple. You have a forward pass, backward pass, you compute the gradients, and then you do the optimizer step to update the model. Then, when we have a lot of data, a big global batch size, you'd like to do of course you can't fit the whole batch in a single forward. So you're going to do it in steps, what we call gradient accumulation. So you're going to do a bunch of forward backwards, sequential. Now comes data parallelism. Since we have independent batches of data, why not do this in parallel? And this is where data parallelism comes. So we're going to give each GPU a different batch of data. So they're going to do the forward, backward in parallel. And then we're going to sync them. So we're going to need to run a communication between the GPUs to sync the gradients to have the same exact training. So the compute communication diagram is going to look like this. You're going to do the forward, backward. This is for each GPU. And then you have this communication step, which is an all reuse. Now what we can see here is that for that amount of time, the GPU stays idle. But that's not why we have GPUs. If we have GPUs, they must work all the time. And luckily, we can use our network while doing computation. So let's try to overlap them. This is where PyTorch DDP comes to the rescue. And it tries to overlap the synchronization with the backward very nicely, thanks to the bucketing system. So the question is, since BP works so well, why can't we just always set BP to the amount of GPUs we have and then launch trainings? Comes the first constraint. We need to satisfy a global batch size. There's some papers that say, so if you train with a bigger global batch size, which is the batch size that you're training on in one iteration step, in one optimizer update step. So the fewer updates, you're going to affect performance, basically. So people usually try and train with a global batch size of like 10 millions of tokens. And so once you set a BP size of 32K, let's say you have 32,000 GPUs, and you use all of them using data parallel, you're quickly going to overshoot that global batch size, and so you're going to affect your performance. And thus, we can not only use one form of parallelism, which is data. So the other constraint is that data parallel assumes that you can fit the model in one GPU. But if you take the Llama 3.3 70 billion model, it cannot be loaded on a single GPU because it takes like 140 gigs of memory. And of course, you're limited by the number of GPUs you own. So the goal is, let's use the available GPUs efficiently to try and train as fast as possible. And thus, we're going to need to optimize our throughput. If we go back to our diagram from before, this is using data parallel, we notice that here, the network is idle. And we said that we can overlap compute and network. So how can we do that? One idea is that why not shard the parameters here and try to overlap the communication? So we try to communicate to the parameters while doing the forward. And this is what 03, or since it's Python today, it's called FSDP. This is what FSDP does. So FSDP shards the model. So let's say you have a big model, you're going to shard its parameters. And then every time you want to do the forward on that part of the model, you're going to fetch it with what we call prefetching. So for example, we're going to prefetch 0, then do the forward, prefetch 1, do the forward, etc. And with this, we can have a nice overlap between compute and communication, even in the forward and backward. And the cluster is happy because it does the work all the time. But we still have the constraint is that it scales with data. So we can't just use FSDP all the time if you have a lot of GPUs. So the other issue is that whenever we use one form of parallelism, let's say DP or FSDP, we're going to go through Ethernet, and so we're not going to use the NVLink connection efficiently. But for example, let's say we have TP8, then the TP are going to use NVLink efficiently, and the rest of the parallelism is going to use Ethernet. And thus comes this. I paid for the whole cluster, so I'm going to use every bit of it. Here comes the second form of parallelism, TP. And the intuition behind TP is that if we take a matrix multiplication, it can be parallelized. And it holds even true like for two matrix multiplications. So each GPU is going to hold half of the weights. And each GPU is only going to do half of the compute, keeping the same data. This is why TP is cool. So for data parallel, we were like sharding the data. For TP, we can use the same data and still split the compute and distribute the compute. But we have a very big, scary communication here that is inside the forward and backward, and thus, and it's inside the critical path. Like you can't continue the forward if you don't do the synchronization. And thus, TP requires very high interconnect. So TP, it's good to shard the model, distribute the compute, and do compute that comes a lot of time. It's actually 4 times each decoder layer. So it helps to overcome the global batch size constraint, but needs high interconnect. The third form of parallelism, CP. CP is used when you want to scale sequence length. Obviously, the memory is going to blow. And CP, what it does is that it's going to shard the data along the sequence dimension. So if you train it with 128K, it's going to shard along that. Which module in the transformer needs the full sequence is the attention. So obviously we're going to need to adapt the attention, which means we're going to do the counts every attention layer. And we're going to need to sync the gradients because every GPU is going to see a different data. And you have a nice diagram of ring attention. For the constant compute, they can be nicely overlapped thanks to the prefetching as well. So while you're doing a online softmax or online computation of the attention with KIVI, you can already fetch the next key and value. And thus it can work nicely, but it requires high interconnect, similar to TP, because you cannot continue the forward unless you get these results. And let's take a small digestion break. For PP, the intuition behind it is that, so you have transformer, a lot of layers, and you can shard across the number of layers. So let's say we have a model which has 4 layers. We're going to put each layer in a GPU, right? we have, of course, our batches, like let's say 8 batches. Then we start with the first batch. We're going to do the forward, send the activation to the second GPU, do the forward, etc. Same thing for the backward. And we do that for all the batches. The problem with PP is that you have a big pipeline bubble, which keeps the GPUs idle, and we don't want that. Unless DeepSeek have came up with this very nice, fancy pipeline scheduler called DualPipe. And as you can see here, there's almost no bubble. So it works very nicely. That's it. And for EP, EP works with MOEs. So for MOEs, you're going to have multiple experts. And the router is going to try to dispatch the token to the correct expert. So obviously, if you have the experts that are sharded, then the router will need to send the correct token to the correct device. So we're going to need an all-to-all here. And after the compute of the FFM. So this is expert parallelism. We're just going to chart the experts, and we're going to adapt the MOE layers, which means we're going to add communications every MOE layer, and that's only used for MOE trainings. And of course, DeepSeek has also granted us a very cool implementation, DeepEP, which overlaps compute and communication very efficiently. 5D in a nutshell, we made a very nice diagram to summarize all of this, where you can find communication at which point CP affects only attention, EP affects only the MLP. Then you have communications that affect parameters, some of them affect activations. This helps summarize it. We also made a cheat sheet, which is the recommendations we use for our trainings. And you can find much more in Narratron, Torch Titan, Megatron Newspeed, and of course the ultra-scale playbook. Finally, as we scale to thousands of GPUs, let's be mindful of their energy impacts and try to use them responsibly, and so try to train or use all of them for the fewest, train as fast as possible, basically, to not waste energy. Thank you.